So ayan, we already defined what is the definition of analysis of structure. So we have found out that analysis of structure is, sa simpleng salita, finding out the individual contribution of each member or parts of the structure as it resists the load it supports. So, okay na tayo dyan sa definition ng analysis of structure. Check na tayo dyan. So, now, dito tayo sa second goal natin for this meeting or discussion. To be familiar with the common types of loading and the techniques on finding the resultant of distributed loading and its location. So, since alam na natin na ang structure, purpose niya, to support a load, so it is worthy to know the different types of loading that we will anticipate na may experience or may encounter ng structure natin as we study the different types of structure in civil engineering, as well as yung technique sa pagkuha ng resultant at yung location nito if we will experience a distributed loading, which is one of the common types of loading that we will study. So these are the common types of loading that we will experience in civil engineering. So ito yung mga madalas nyo ma-encounter habang nag-aaral kayo ng civil engineering. Una is yung tinatawag natin na point load or concentrated load. So paano yung itsura ng point load? So obviously it is a load. Yan. Load acting on a single point. Or in other words, a load which is concentrated in a point. That's why it's called point load or concentrated load. So, madalas, may encounter niya. And actually, ng static sa rigid bodies nyo, malamang puro ganyan yung na-encounter nyo na type of loading. A load acting on a single point or concentrated lang siya sa isang point. Pero, sometimes, you will encounter a load that is not acting on a single point or not concentrated on a single point or single area. Kumbaga, acting siya on in a surface, for example. So, sometimes makaka-encounter kayo ng ganong type of loading na instead of acting over single point lang, it's acting over a surface. So, ang tawag sa ganong type of loading, acting on a surface, is what we call distributed loading. So, yung mga distributed loading na yan, usually, ma-encounter mo yan. For example, kunyari, meron kang sign. Kunyari, yung no parking sign sa kalsada. Tapos, kunyari, humangin. So, yung hangin, pag tumama dun sa sign, hindi lang naman siya sa isang point tumatama dun sa sign, di ba? Hindi lang naman siya sa na-concentrate sa isang maliit na area dun sa buong sign. Actually, the wind pressure is acting all over the whole surface of the sign. So, ang tawag doon sa ganong type of loading, acting on the signboard, is, again, distributed loading. Bakit distributed loading? Because it is acting not only on a single point, but over the whole surface. So, another example of distributed loading na may encounter nyo is yung pressure of water within a tank. So, kunyari, meron kang tank, may lamang tubig sa loob. Tendency, ginagawa ng tubig sa loob ng tank is tinutulak niya palabas yung inner wall ng tank. Kaya, kumbaga, ina-apply niya ng pressure yung inner wall ng tank. So, if you can imagine, yung pressure na ina-apply ng water dun sa loob ng tank is acting over the whole inner surface wall of the tank. So, again, it is an example again of a distributed loading. So, last example is, kunyari, meron kang buhangin or sand na nakasalansan dyan sa lapag. So, yung bigat ng sand, hindi lang siya nakakonsentrate sa isang small area, bagkus naka-distribute siya over the whole surface of the floor. So, ibig sabihin, again, that is an example of distributed loading. So, in general, distributed loading, it is a load usually distributed over a surface. So, hindi lang siya naka-concentrate sa isang small surface or isang small area. So, yun. For you to better visualize ano ba yung itsura ng distributed loading, let's say for example, I have here a force acting on a very small surface or very small length. Let's just call that very small length dx, because usually naman sa calculus, when we represent very small length, we usually call it dx or differential x. And for example, meron siya rin siyang katabi na ganun din, same force acting on a very small length. And meron na namang katabi na force acting on a very small length. And meron na namang katabi. Yan, ganyan. So actually, that is what it's look like to have a distributed loading. There is a load acting on a surface or a length. So say for example, yung total length niyan, since this is dx, so total of n dx, wherein yung n is kung ilan sila, kung ilang dx yan. So yung n natin dito, kung mapapansin nyo, that is a counting number. So what are counting numbers? So usually yun yung mga 1, 2, 3. So counting number lang yan, and it represents kung ilang very small length nag-act yung mga maliliit na force na to. So, kung merong limang dx dyan, ibig sabihin yung total length niya is 5 dx. Although in this case, just to make it more general, hindi ko na siya lalagyan ng specific na value, hindi ko na bibigyan ng 5 dyan. So, gagawin ko na lang general. Let's just call that n. So, yung ganyan, yan yung tinatawag na example of distributed loading. Although in this particular case, merong specific na tawag sa kanyang distributed loading. And ang tawag dyan sa ganyang distributed loading ay uniform load or uniformly distributed load. So, bakit tinawag na uniform load or uniformly distributed load? Obviously, kasi parang uniform yung magnitude ng mga force acting on a very small length. So, obvious naman na equal or uniform yung mga magnitude nila. So, kapag ganun yung case ng distributed load, it is not only called distributed load, but uniformly distributed load or simply uniform load. Now, say for example, we want to find the resultant of these several forces acting on this surface or length. Paano natin makukuha yung yung resultant niyan, yung several forces na yan. So ngayon, ituturo ko lang yung underlying concept doon sa pagkuha or sa technique ng pagkuha ng resultant ng distributed loading. So actually, kung ikaw, isa kang estudyante na medyo ayaw mo nang malaman yung concept behind the technique, hindi ka mahilig na mag-check pa nung mga concepts na gano'n, yung mga theories, kung bakit naging gano'n yung technique, at this point, pwede mo nang i-skip tong part na to. So, dumiretso ka na dun sa part na sasabihin ko na yung mismong technique. So, para hindi na rin sumakit yung ulo mo, hindi ka na rin maguluhan. Pero kunyari, kung ikaw naman yung estudyante na medyo gusto mo pang malaman, bakit naging ganun yung technique? Bakit bigla na lang ganun yung technique? Ano yung underlying concept? Bakit naging ganun yung technique? So, kung ikaw yung ganung estudyante, diretso ka lang sa pakikinig, sa panonood. So, yun. So, yun yung goal natin ngayon. Gusto natin makuha yung resultant nitong several forces na to acting on this surface or length. So, paano natin kukunin yun? So, from statics, alam natin na if you want to get the resultant of forces, all you have to do is vector add them. So, add lang natin yung mga magnitude nila. Although, in this case, since same naman lahat ng direction nila, kahit i-arithmetic add na lang natin siya, okay lang yan. Since obvious naman kung ano yung magiging final direction na resultant, which is obviously downward kasi lahat naman sila downward. So, paano natin makukuha yung summation yan? Paano natin ipag-add yan? Yung mga several forces na yan. So, ito yung analogy. If there is a force acting on very small length, dx, ibig sabihin, meron kang force per dx, merong force na ganito kada dx, and there is a total of n dx. Therefore, ilan lahat ng force na yan? Kung merong r over n na force per dx. So, paano mo makuha yung summation ng mga force na yan? So, all you have to do is multiply this to this para makuha mo yung summation nitong mga forces na to. Or, kung gusto mo ma-visualize kung paano yung pagkuha ng resultant, so from statics lang din, paano mo mag-add, merong dalawang method ng pag-add from statics, analytic method, tsaka graphical method. So, in this case, pinakita ko lang yung graphical method, which is, actually, this is tip-to-tail method. So, sa tip-to-tail, ang ginagawa lang, yung tip nung first na force or vector, dinudugtong mo lang dun sa tail nung sumunod, and so on. And then, paano mo makuha yung resultant? Yung resultant is yung force or vector na mabubuo kapag connect mo yung tail ng una sa tip nung huli. So, ano yung sum nitong several forces na to? That is just equal to, sabi ko nga kanina, that is just equal to the product of this and kung ilan sila. So, that is just r over n over dx times n dx. And that sum or product is just equal to the resultant of these several forces. Actually, pag sinimplify mo to, dx cancel. May n sa denominator, may n sa numerator, cancel. So, matitira na lang ay r. So, that is actually the resultant of these several forces. Although, in this case, medyo parang ang haba tignan nitong r over n over dx eh. Diba? So, siguro pwede na lang natin gawin yan na instead of that, tawagin na lang natin siya na w, for example. Ito, tawagin na lang natin siya na simply L. So, ibig sabihin, pwede natin itong palitan ng W, pwede natin itong palitan ng L. So, ibig sabihin lang nun, resultant is also equal to WL, wherein yung W is this, and yung L is this. So, yun, nakuha na natin yung resultant nitong distributed loading na to. So, ito yung resultant niya. Kaso lang, may problema. Hindi natin alam kung saan ba siya specifically located over this surface or length. Dito ba siya located? Dito ba siya located? Dito, dito. So, di natin alam. So, paano natin malalaman yun kung saan siya actually located? Pwede natin gamitin yung concept ni Varignone, yung Varignon's theorem. So, ano ba yung sinasabi ni Varignone sa Varignon's theorem? Sabi ni Varignone sa Varignon's theorem, sabi niya, kung ito daw ay resultant netong several forces na to, therefore, dapat yung moment nitong resultant na to with respect to certain points. Say, for example, dito sa edge na to, dapat yung moment niya dito sa edge na to, so paano ba kumuha ng moment? Moment is just equal to force times moment arm. So, ito na lang yung moment arm natin. Tuwagin na lang natin yung x-bar. So, sabi ni Barignon, if sinasabi natin na ito ay resultant nitong several forces na to, therefore, dapat yung resultant nito with respect to this certain point, which is this, force times distance. Yung moment na yan, sabi ni Barignon, dapat equal lang sa summation ng mga moment nitong mga component nitong resultant. So, ibig sabihin, dapat, pag minoment natin itong mga to, mga yan, with respect to this same point, same lang yan, pag minomet natin yung mga forces na yan with respect to this same point, at pinag-add natin lahat ng moment na yon, which is this, ito yung lalabas, dapat daw yung summation yan, sabi ni Barignon, equal sa moment nung resultant force with respect to that same point. Kung sinasabi natin na ito ay resultant talaga nito. So, paano nakuha to? Paano nakuha yung mga terms na to galing sa pag-moment nitong mga forces na to with respect to this? So, unahin natin, i-moment itong force na to, yung r over n na to. So, moment is equal to force times distance. This is the force, so r over n. Ano yung distance niya with respect to this? If this is dx, and obviously, ito ay located sa middle, sa midspan, kumbaga. Therefore, itong distance nito ay kalahati ng dx. So, that's the first moment. Second moment is this, again, force times perpendicular distance. So, ano itong perpendicular distance na to? This is just dx plus kalahati ng dx. So, 1 plus 1 half is equals to 3 half dx. And so on. And so on. So, kung sundin mo lang yung pattern, makakarating ka dito sa dulo. Ito yung moment nung nasa pinakalas with respect to this same point kung saan mo minoment tong resultant na to. So, ipag-add mo yan, dapat daw, sabi ni Barignon, yung sum na yan equal sa moment nung resultant with respect to that same point. Ngayon, baka may magtaka sa inyo, paano ko nakuha tong 2n minus 1? Observe nyo lang, tignan nyo itong numerator na to. 1, 3, 5. So, parang may pattern, di ba? So, alin kasunod ng 5 malamang? 7, 9. Para siyang may pattern. Actually, para siyang nakagawa ng progression eh. Actually, that is a progression. And that is actually what we call arithmetic progression. Bakit siya tinawag na arithmetic progression? Kasi, ano siya, parang progression siya na may common difference. In this case, ano yung common difference natin? 2. 3 minus 1, 2. 5 minus 3, 2. 7 minus 5, 2. So, may common difference tayo. So, paano makuha yung last term sa isang arithmetic progression? So, recall ko lang kung paano makuha. So, from saan ba inaral to? Siguro sa Advanced Engineering Mathematics. Sabi doon, kung meron kang arithmetic progression, yung last term is just equal to the first term, which is 1, plus the product of the common difference, which is 2, times n minus 1, wherein yung n is yung number of terms. So, in this case, yung n naman represents the number of terms dito. So, leave as is mo na lang siya. So, substituting those values, lagay mo dito 1, lagay mo dito 2. So, ang lalabas is this. And then, pag sinimplify mo yan, ang lalabas is 2n minus 1. So, ibig sabihin lang yung last term dito sa progression na to is just equal to 2n minus 1. So ganun ko nakuha to, yung 2n minus 1 na to. So, simplifying, kasi may r over n tsaka dx bawat term eh. Yan, kung mapapansin nyo, may r over n tsaka dx kada term. So, pwede natin i-factor out yan. Factor out that, ang matitira na lang sa loob ay 1, 3, 5, and so on hanggang 2n minus 1. So, paano mo isi-simplify ito, yung nasa loob ng quantity na to? So, again, that is just a sum of arithmetic progression. And recall lang natin ang formula sa sum ng arithmetic progression. Sum is equal to sum ng first term tsaka last term times kalahati ng number of terms. So, that's a direct substitution lang to. What is a sub 1? First term is 1. Last term is 2n minus 1. So, substitute mo lang yan dyan. Ito yung lalabas. And then, simplify na lang natin. May r sa left side ng equation, may r sa right side. So, cancel. Cancel yan. Ito, 1 minus 1. So, 0. 2n, n over 2. Cancel yung 2. Matitira na lang sa loob ng quantity is n times n. May n sa denominator. So, matitira na lang ay, ito, 1 half n dx. So, sa right side, mawawala ni r. So, x bar na lang yung matitira. Since n dx is equal to L, therefore, we can change this to L over 2. So, ibig sabihin pala, for this resultant to be actually the resultant of this distributed loading or several forces, dapat located siya L over 2 mula dito sa edge na to. So, pag ganyan na yung case, ibig sabihin, itong system of forces na to at system of force na to ay equal na base sa statics. Kasi diba sa statics sabi natin, yung dalawang force system, masasabi lang natin na equal if, number 1, kung yung resultant nila ay parehas. In this case, obvious naman na parehas. Tapos, number 2, dapat yung resultant moment nila ay equal lang din. So, ano ba yung resultant moment nito mga to with respect to this? Eto. Ano bang moment nito dito? Same point. Eto. And obviously, base dito sa equation natin, yung summation ng mga resultant nito, summation ng mga moment nito, equal lang sa moment ng resultant. So, ibig sabihin lang nun, this system of forces equal dito sa system of force nito. So yun, nakuha na natin yung resultant nito. Itong distributed loading. Kaso parang ang dami pinagdaanan, no? Parang ang sakit sa ulo eh. Baka pwede natin gawa ng technique. No? Gusto nyo ba yung may technique? May shortcut, kumbaga. Parang ang sakit na sa ulo pag ganito kahaba yung ginawa mo eh. So gawin na lang natin ganito. Itong pressure diagram na to, ito, other term din dito sa distributed loading nito is actually pressure diagram. So, bakit pressure? Kasi meron kang force acting on a very small surface or length. So, pressure diagram yung tawag dyan. Ngayon, para makagawa tayo ng technique, gawin natin ganito. Let's try to treat this instead of pressure diagram, instead of something that is composed of several forces. Gawin natin, i-treat natin siya as a geometric shape. Geometric shape wherein yung dimension niya is itong length na to, kung saan nag-act yung several forces. Tapos yung height niya is yung magnitude ng pressure or yung force acting on a very small length. So, yun yung gawin nating dimension ng geometric shape natin. So, instead of i-treat natin siya as pressure diagram composed of several forces, i-treat na lang natin siya as geometric shape na may dimension na ganito. So, separate lang natin yan dyan para mas malinaw yung discussion. So, mag-focus tayo ngayon dito sa geometric shape na nagawa natin coming from the pressure diagram. Ano ang area nitong geometric shape na to? This is just a rectangle. Ano ang area ng rectangle? Obviously, it's just base times height. So, product lang nitong dalawang dimension. So, therefore, ang area is equal to product of this and product of this. That is the area of this geometric shape. Or, since ito ay equal lang naman sa W, and ito ay equal sa L, therefore, area is also equal to W times L. Or, kung isi-simplify mo to, this is just equal to R. So, ang area nitong geometric shape na nabuo natin, coming from the pressure diagram, ay equal lang dito sa mga to. Now, yung centroid naman, pag-usapan natin. Rectangle. Nasaan ang centroid ng rectangle? Sabi sa statics of rigid bodies. So, sabi sa statics, kung meron kang rectangle, yung centroid niya, with reference dito sa left edge, located yung centroid sa kalahati ng length. So, kung ang length natin ay L, therefore, ang location ng centroid natin is kalahati ng L, which is L over 2. So, again, yung area nitong geometric shape na to, coming from the pressure diagram, ay equal dito. And yung centroid nitong geometric shape na to ay equal dito. Ngayon, nandito yung technique. Observe nyo lang. Ito yung resultant nitong distributed loading na to. Yan yung napatunayan natin kanina. Yan yung nakuha natin kanina. Kaso lang, tingnan nyo. Try to compare yung values niya dito sa area nitong geometric shape na to. Compare nyo lang. So, anong observation natin? Anong masasabi nyo? Parehas lang. Same value. Same value yung resultant ng distributed loading na to sa area nitong geometric shape na to when we treated the pressure diagram as a geometric shape. As well as, tingnan nyo to, yung location ng resultant na to. This is L over 2 from the edge. Tingnan nyo yung location ng centroid ng geometric shape. L over 2 rin. Ano ba yan? Nagkataon lang ba to lahat na yung location ng resultant tsaka yung location ng centroid nitong geometric shape na to equal? Nagkataon lang ba yan? Actually, hindi. Hindi po yan nagkataon. Actually, that is the technique that we want to na ma-formulate dito sa discussion natin. So, in conclusion natin, base sa observation natin, in general pala, the resultant of any distributed load is equal to the area of the pressure diagram treated as a geometric shape acting at its centroid. So, anong ibig sabihin nun? Ibig sabihin lang nun, kung meron kang distributed load dyan, and you want to find the magnitude of its resultant as well as its location, all you have to do is Instead of treating this as composed of several forces, treat it as composed of a geometric shape with this dimension, and then yung resultant netong distributed loading na to is just equal to the area nitong mabubuo mo na geometric shape. And saan located yung resultant na yon? Yung resultant na yan, that is just located sa centroid nitong nabuo mo na geometric shape. So, yun yung concept na or yung technique na makukuha natin dito sa discussion natin na to. Ibig sabihin lang nun, if you want to find the resultant of this distributed loading, hindi natin kailangang pagdaan yung pinaggagawa natin kanina napakahaba na may mga arithmetic progression pa. Ang kailangan na lang natin, itong pressure diagram, i-treat natin as geometric shape. Yung area ng geometric shape na yan, that is the resultant of the distributed loading. And yung location ng resultant na yun is just equal to the location nitong centroid nitong geometric shape na nabuo natin. So actually applicable yan sa kahit anong any type of distributed loading, kahit anong itsura, applicable yung ganyan technique. So try natin i-apply yung technique na buo natin yan. Say for example, meron ako ditong distributed loading ulit. Several forces acting on this length. Say for example, length L. Meron akong distributed loading acting on a surface or length. Pero yung magnitude ng mga load na nakadistribute, obviously, hindi na siya equal or pare-parehas. Unlike this, kanina pare-parehas eh. So, hindi na siya pare-parehas. Actually, it varies na. At it varies along the length. And specifically, it varies linearly kung mapapansin nyo no? Parang linear lang eh. So, yung pagbabago ng magnitude ng pressure na yan per length is nagba-vary linearly. So, hindi na siya uniform katulad nito. Actually, may tawag sa ganitong type ng distributed loading. Ang tawag sa ganyang type ay triangular load or linearly varying distributed load. So, bakit triangular? Obvious naman, kasi hugis, triangle. Bakit tinawag na linearly varying distributed load? Kasi obvious naman din, yung magnitude ng force per length, nagva-vary siya linearly. So, say for example, yung magnitude nitong pinakamalaking pressure dito sa distributed loading, tawagin na lang natin na W. And then, gusto natin kunin yung magnitude ng resultant nitong several forces na to acting on this length or surface. Paano natin makukuha yung magnitude ng resultant ng maraming forces na yan? Again, pwede mong gawin yung pinaggagawa natin dito kanina. Isa-isahin mo yan, tapos ipag-add mo, tapos i-moment mo pa dito para makuha mo yung actual location ng resultant. Pwede mong gawin yun. Or pwede mong gawin yung technique na nabuo natin. So, instead of i-treat natin to as pressure diagram composed of several forces, treat na lang natin siya as a geometric shape na may dimension na ganito. So, ihiwalay ko lang yan. Nakabuo na tayo ng geometric shape. So, instead of treating it as pressure diagram composed of several forces, treat na lang natin siya as a geometric shape. Now, nabuo nating concept is yung resultant daw nito equal lang dito sa area nito. Yung nabuo natin na geometric shape. And this geometric shape na nabuo natin is just a triangle. So, yung area ng triangle is just 1/2 base height. So, ibig sabihin lang, yung resultant na itong maraming forces na to, itong distributed loading na to, is just equal to this, the area of this geometric shape, which is just equal to 1/2 base height or 1/2 WL. So, napakabilis. Nakuha natin agad yung resultant nitong distributed loading na to without na pinagdadaanan pa yung madami pinagdaanan natin kanina dito. And yung location ng resultant na to, saan siya actually located? Again, doon siya located sa centroid ng nabuo natin na geometric shape. So again, triangle yung geometric shape natin, and from statics, sabi sa statics, sa topic ng centroid, ang centroid daw ng triangle, with respect dito sa height, ang centroid daw ng triangle, located 1/3 no length na to. So kung length na to ay L, therefore yung 1/3 niya is L over 3. So, ang location ng centroid ng triangle from the height is just 1/3 no base. So, L over 3 lang siya. So therefore, yung resultant pala nitong distributed loading na to is just equal to 1 half WL located L over 3 from the edge na to. So nakuha na natin agad yung resultant nito as well as its location. Nang ganun kadali. That is the technique I want you to absorb mula ngayon. So magagamit nyo yung technique na yan mula ngayon hanggang sa mag-5th year na kayo, mag-4th year na kayo, or hanggang makapagtapos kayo ng civil engineering. Magagamit nyo yung technique na yan. So again, yung technique na yan, it requires knowledge ng pagkuha ng area as well as the centroid of a geometric shape. So dapat alam nyo yung formula sa area at location ng centroid ng iba't ibang shapes or geometric shapes. So just to help you para ma-familiarize kayo din sa mga area and location ng centroid ng different shapes, naglagay na lang din ako dito ng summary ng area ng mga common shapes as well as yung location ng centroids nila. Actually, itong table na to, kompleto na to. Nandito na yung location ng centroid, nandito na yung moment of inertia ng different common shapes na to, nandito na rin yung area nila, yung mga hindi masyadong common. So, nandito na lahat. Technically, nandito na lahat. Yan. So, pwede nyo itong gawing reference sa buhay nyo, sa pag-aaral nyo ng civil engineering. Although kung may hindi man completed, kung may kulang man dito, edi ano na lang, i-supplement nyo na lang.